Okay, so this video is for OCR B, and I'm going to waffle on about the Advance Notice article 2025. So this is my thoughts on it. I've had a good read of the article. What kind of things might it ask questions on? So just a reminder, paper 2 hours 15 minutes, 100 marks, which is 37% of the exam, the whole course. All of the course can be assessed on this paper. However, there is an emphasis on scientific literacy, which I think that means comprehension, so understanding stuff written in a scientific way. Section C is what we're interested in here. Now, I say it's only 25 marks. However, it's the only part of the paper that you can really prepare for by kind of trying to predict what questions will come up and revising certain things. You should be given your copy of the Advance Notice article. You should have it by now. If you haven't, you then find it on the OCR website. You'll be given a new copy in the exam. So, capturing the moment, it's all about recording sound, different types of microphone. The very first recorded sound was this thing, the Phonoautograph in 1859, and it produces a visual record. Now, why can't you play it back? And I think it's really, if you think about it, it's basically making scratches on soot, a glass surface covered in soot. Now, how is a stylus going to read that? Apparently what they've done is they've taken photographs of it, of these recordings, and then etched it onto metal, and then played that back. And you go on there's a link in the article and have a listen. It's quite amazing. There's a very large horn which collects lots and lots of sound. There's a diaphragm which will oscillate, will vibrate. The stylus, the bit that does actually makes the mark in the soot, is they used a boar's bristle, apparently. The moving glass surface, when you turn the handle, then the stylus moves across it at 1 meter per second, about, and it produces a trace, like something like an oscilloscope trace. Now, the horn funnels the sound waves onto the diaphragm, and that increases the amplitude. Maybe something to do with intensity, increasing the intensity, which is power divided by area, watts per meter squared. So if there's the same amount of energy, the same amount of power over a smaller area, then you're going to get more intensity, so you get bigger amplitude. One thought struck me is that the diaphragm, now it's longitudinal waves, isn't it? So the diaphragm will be kind of vibrating in a kind of a longitudinal manner, but you want to record like a transverse wave. So have a little think about that. I think my diagram here, it's not clear on their diagram, something like that going on, yes? Where the boar's bristle scratches the soot. Why a boar's bristle? Why does that make a good stylus? Maybe something to do with materials here. Maybe it's strong, so it won't break easily. It's stiff, it's tough, so it's resistant to cracking. And obviously its dimensions, it has a nice sharp point to do the scratching with. Maybe some kind of oscilloscope question. It does mention an oscilloscope. So, you know, if that's the trace there, let's say for a frequency of 400 hertz or whatever, what's the period? What's the wavelength? Maybe getting it off a diagram like this, maybe an oscilloscope question showing that you understand the time base on an oscilloscope. Signal to noise ratio. Now, what does that mean? Well, it's the amplitude of the signal divided by the amplitude of the noise. So the bigger the signal to noise ratio, the better. Now, in this particular case, what noise are we talking about? Well, external vibrations, vibrations in the machine, any vibrations other than those that you want to record. Yes, and that's noise. You don't want it there. So that's signal to noise ratio. I know this comes up in the digital signals bit as well. Maybe a question to do with that. Seems a little bit vague getting digital when we're talking about this machine. Now, so different types of microphones, dynamic microphones, a coil and a magnet. So the coil moves and we get an induced EMF. From Faraday's law, the induced EMF is proportional to d phi dt, or this equation here, induced EMF is minus d n phi dt, where n is the number of turns, phi is the flux, minus sign is there because of Lenz's law. Now, the coil has to move in and out of the field. Now, why? Because the flux linkage has to change. Yes, if the amount of flux going through the coil doesn't change, you're not going to get an EMF, are you? So the coil has to move in and out of the field. The flux linkage and the EMF are going to be 90 degrees out of phase. Okay, it mentions phase. This will come up. Why are they 90 degrees out of phase? Well, okay, so if the flux linkage varies sinusoidally, then we can write something like n phi is n phi naught sine omega t, where omega is the 2 pi f, where f is the frequency. Now, if we differentiate that, then we also have to put the negative sign, as mentioned before. Then we get the EMF as being a negative cosine. Yes, so if you look, so n phi I've got as a sine, the EMF as a negative cosine. The maximum EMF will be when cos omega t equals 1, so that will just be n phi naught omega, and n phi is BAN. How might we get a bigger voltage output? Well, look at the equations. How might you do it if you had a stronger field, if B was stronger, if you had a bigger area, if you had more turns? And then obviously it will depend on omega as well. Yes, because d phi dt will be bigger if the frequency is bigger. Phase difference. Is this phase difference a problem? Well, sometimes it is in a recording studio if you're using several microphones and they're out of phase with each other. And then when you're mixing the signals together, maybe you're going to end up with destructive interference. And this is the kind of thing that recording engineers need to think about. They have to worry about the phase difference due to this kind of thing. They've got clever, expensive boxes which can fix it. But anyway, there you go. Now, some components have natural frequencies, resonance. Learn this. Resonance. When the driving frequency is equal to the natural frequency of a system, it results in large amplitude oscillations. That's resonance. For a mass on a spring, I dare say this is not going to be a pendulum, it's a mass on a spring. You've got your T is 2 pi root m over k, so the natural frequency will be 1 over 2 pi root k over m, where k is the stiffness of the system and m is the mass. So we're talking the diaphragm and the coil having their own natural frequencies. How do we reduce that? Well, we can increase the amount of damping by increasing friction, and then you're losing energy every cycle due to friction. Or if you change the natural frequency of the components involved to a frequency where it doesn't matter. Yes, perhaps make the masses bigger, and that will make the natural frequency smaller. Yes, so either that or change the stiffness as well. That would have an effect. I mentioned the sound box in a guitar. Now, what does that do? It's designed to resonate. The actual wood and the air inside resonates at lots of different frequencies so that you get a flatter response. In other words, there aren't any particular frequencies, and also it tends to increase the amplitude of the lower frequencies. And this will affect the tone of the sound. The tone is the harmonics involved. Yes, so that in terms of a guitar, that's what it's all about. Anyway, this is now what's this? Frequency response, sensitivity. Sensitivity is the change in output divided by the change in input. In this case, it's the voltage output in millivolts against over the pressure difference, which is in Pascal. So millivolts per Pascal. Typically for one of these microphones, we're talking about 1 to 4 millivolts per Pascal. This scale here, however, they're using decibels, which is a logarithmic scale. Yes, I'm not sure you need to worry too much about converting millivolts per Pascal to decibels. Notice that the frequency is also a logarithmic scale. Why do they use a logarithmic scale? Yes, because there's such a huge range of frequencies. To display it meaningfully, they use logarithmic scales. Why does the sensitivity get smaller? It says it drops off rapidly after 16 kilohertz, and by the time you get to 20 kilohertz, the sensitivity is rubbish. Now, why does it get less? Because a larger mass has a smaller acceleration for the same force. So at higher frequencies, we're asking for bigger accelerations from a big mass. So you're not going to get bigger accelerations, are you? Because it has a large mass. Now, higher note on a piano is about, it says 4,400 hertz. Now, that's not a problem, is it? Because it doesn't drop off till 16. However, this piano note will contain lots of harmonics. Its tone, what the piano sounds like, isn't just the fundamental frequency. It will be all of these harmonics. And on a string, on the piano string, we know that the harmonics are going to be multiples of the fundamental, aren't they? So you're going to get your 8,800, etc., etc. There's a frequency spectrum there, and we don't want to be losing too many of these higher harmonics. Condenser microphones. So a condenser is a capacitor. It's what Americans call a capacitor. So capacitor microphones. C is epsilon naught, epsilon r, A over D. Maybe working that out, you know what all those bits stand for. Now, if it's an air gap, and it says it's an air gap in the text, the relative permittivity of air is very, very close to 1. So it may as well just be epsilon naught A over D. Now, looking at the diagram here, what happens is that the voltage across the capacitor stays the same. So as the diaphragm moves, as the gap, so the diaphragm moves inwards, it's pushed inwards, the capacitor charges up, more charge comes on it, but because its capacitance gets bigger, the charge gets bigger, the voltage stays the same. So as a current flows on, then you're going to get a voltage across this resistor. So you're going to get an AC current flowing in this circuit as it charges and discharges, an AC voltage across the resistor. Okay, so make sure you understand how this actually works, this capacitor microphone. So condenser microphones or dynamic, advantages, disadvantages. Well, the condenser microphone, the membrane has a small mass, a smaller mass than the coil, so the microphone is more sensitive to higher frequencies. Remember, we discussed why that was a problem. And also the signal is in phase with the sound, so that avoids some of the other problems we were talking about. Disadvantages, it's much more delicate. It's a very thin membrane, and you need this bias voltage, this what we call phantom power. I need it on the microphone I'm using at the moment. So you need this bias voltage for a condenser microphone. Now, Electret microphones. To be honest, until I saw this article, I'd never heard of these, but I've been doing some reading about them. Very interesting. They're small microphones, high sensitivity, very good frequency response. used in things like laptops and smartphones and professional recording equipment as well. Very interesting. So Electret microphones. There's a diagram there. If we look here, so we've got this Electret material, which is a membrane, and that's what vibrates when sound hits it, this Electret material. Now, the thing is, it has a certain amount of charge on it, positive and negative. So if you like, my red is positive, my blue is negative, and that charge stays the same. It's isolated, yeah, it's insulating spacer there. That amount of charge stays the same. It doesn't change. Now, what happens is that this negative charge underneath will pull positive charge up from the metal backplate. So what we have is we have two capacitors. We've got the Electret material, which is this membrane, is like a capacitor on its own, because it's got like, look, it's got positive, negative charge with a material in between. And then the air gap is another capacitor, because you've got this, you know, that look, there's your blue negative at the top, so, and then red positive, so two capacitors, and there's the equations there to work out their capacitance. Maybe you'll do a bit of bunging in the numbers using those equations. Okay, now the charge on the Electret does not change, so when the capacitance changes, as D changes, then the voltage will change, and that is our signal. Yes, they pick up the voltage from the metal backplate. Capacitors in parallel, capacitors in series. This isn't on OCR B, so I'm talking about it here. Capacitors in parallel, you just add the capacitors together. It's the opposite of resistors. Yeah, resistors in series, you add them together. Capacitors in parallel, you add them together. Because basically you're just increasing the surface area, so you're increasing the amount of charge it can store. Now, capacitors in series is, again, it's the opposite of resistors. Now, what happens here is that the charge must be the same on both capacitors. Why? Because if you think about it, the charge on the second capacitor, where does it come from? It came from the first one. Yes? So the charge must be the same. The voltages will be different, but the charges must be the same. Now, our Electret capacitor is apparently like the two capacitors in series, okay? Because the charge on both of the capacitors must be the same. MEMS, again, a really interesting article, and I've been doing a bit of reading about MEMS, and it's not just capacitors. There's a huge range of these tiny little electromechanical components. Have a look on Wiki, there's a massive list of MEMS, all kinds of stuff. One of them is capacitors, tiny capacitors. Okay, if you think about in your mobile phone how big that microphone is, I'm predicting some kind of question to do with working out, maybe estimating the size of the capacitor from an image, maybe something to do with resolution and digital images and that kind of thing. Yeah, what distance does each pixel represent? Yeah, very interesting. MEMS. So if you've got any other ideas, then put something in the comments. And I'm sure people will appreciate that if you do, and good luck in the exam.